Welcome to the Introduction to Correlated Materials, a series of lectures to help you understand and admire the role of electron-electron interactions in solids. Brought to you by Schrodinger's Kittens Productions. Beyond band theory. We know already quite a few examples of where simple band theory predicts a metal but a more sophisticated treatment will give us an insulator. The first example that comes to mind would be if we have to consider magnetic ordering. So for example, if we have a 3D transition metal or a 3D transition metal compound with a 3D band and say 5 electrons, if we don't consider the magnetic ordering, then the 3D band would be half filled. But once we consider the magnetic ordering, then we have a band for upspin electrons and a band for downspin electrons, which are separated by the exchange interaction. And the upspin band would be filled and the downspin band empty, separated by a band gap. So here, the simplest possible band theory that doesn't take into account that the electrons are magnetic would give us a metal, but a more sophisticated treatment that accounts for the magnetic exchange gives us an insulator. A second example from transition metal compounds would be the crystal field splitting. And so, for example, if we had a system with 3 3D electrons in an octahedral crystal field, so octahedrally coordinated by oxygen anions, say, without considering the crystal field splitting, then the d electrons would all have the same energy. And even considering the magnetic ordering, the band would be 3/5 filled. Whereas with the crystal field splitting, we know that the energy levels split into a T2G and an EG level, and our 3 electrons would fill the T2G and they'd be separated by the crystal field band gap. So again, the simple picture that doesn't take into account the crystal field splitting would give us a metal, and the more sophisticated treatment would give us an insulator. Let's remind ourselves of a couple more examples. The third one would be the Jahn-Teller distortion. And this is an example where we have to take into account coupling between the electronic structure and the lattice to correctly get an insulator in the situation where trivial band theory would give us a metal. And here an example would be a transition metal compound with 4 3D electrons in an octahedral crystal field. The example that we just looked at, the crystal field would split the T2G and the EG energy levels, but we would have a half-filled band unless we take into account the Jahn-Teller distortion, which splits the energy levels so that we have, again, in this case, a Jahn-Teller band gap. So this is an example where coupling to the structure turns what in the simple picture would be a metal into an insulator. And then the last example I wanted to remind us of is the piles instability. Which is again a coupling between the electronic properties and the physical structure. And the piles theorem tells us that a one-dimensional metal is always unstable to a structural distortion that opens a band gap. So these are all examples in which, if we just took the simplest possible band theory, we would end up assuming that our material was a metal, whereas in fact there's some other driving force, some other piece of physics, which means it's an insulator. What we're going to start discussing today is another scenario or another physical underpinning that can turn a metal into an insulator, which is the case where the Coulomb repulsion between the electrons cause insulating behavior. Again, in situations where simple band theory would predict that they should be a metal. So here we're looking really explicitly at a many-body electron-electron interaction, the Coulomb interaction between electrons, which is not something that's incorporated in the simplest possible band theory. Okay, so here we go. So the first question we want to answer then is, where does band theory break down? And we're going to do a simple thought experiment where we look at a one-dimensional chain of evenly spaced hydrogen atoms each with a single 1s orbital. And each with a single electron. So this is the example that we chose when we first looked at building band structures in our linear combination of atomic orbitals theory. It's the simplest possible example for understanding how energy bands form in solids. And what we're going to do is gradually increase the spacing between the atoms. And we want to see what happens in our simple band theory picture when we do that. Now, first of all, if we think about what happens in reality, we know that if our hydrogen atoms are infinitely far apart, then each hydrogen atom is going to have one electron, and we'll just have a collection of isolated individual hydrogen atoms, and the system will be insulating. There'll be no transfer of electrons from one hydrogen atom to another. But what we'll see is that our band structure doesn't give us that situation, and this is where this is really the origin of the breakdown of simple band theory. Okay, but let's make a quick review first of simple band theory, and we're going to use our linear combination of atomic orbitals band theory and remind ourselves at this simple band theory level what we expect to see. So we have our one-dimensional train of hydrogen atoms, each with a 1s orbital. Let's space them a distance a apart, and I'm not going to rederive this, but you should remember that the wave function is a function of x. orient our orbitals along the x direction. And it depends on the wave vector k, and it's given by the sum over e to the I k n times a times phi sub n of x, where the n value here labels the number of the atom. So our wave function is a block state, and it's a function of position, a function of x in this case, because we have a one-dimensional system, and it's labeled by the wave vector, the k value. And then the energy of a particular state, a particular orbital with a particular k value, which doesn't depend on x, just an energy, sorry about that, is then given by the integral of the complex conjugate of the wave function times the Hamiltonian operator times the wave function with that k value, normalized by the inner product of the wave function. And this integral in this case will be over x because we're in one dimension. If I substitute this form for the wave function, then our energy is 1 over n, where n is the total number of atoms. Sum over n is equal to 1 to n. Let's give our two wave functions two different labels so that we don't lose track. E to the I n minus m ka times the integral, the 1s orbital on atom m complex conjugated times the Hamiltonian times the 1s orbital on atom n integrated over all space. And in the usual tight binding approximation, we say that this integral is equal to alpha if m is equal to n, n is equal to beta if m and n are nearest neighbors. And so our expression simplifies to alpha plus 2 beta cosine Ka. So the energy of the kth energy level is equal to the energy of an isolated hydrogen atom plus a term which depends on how strongly the adjacent hydrogen atoms are interacting with each other. And in particular, this gives us a bandwidth of 4 times this interaction strength. And because we have 1 electron per atom, and each energy level could take 2 electrons, this gives us a half-filled band. Which of course is metallic. If you're paying attention, you might have noticed that we've ignored the fact here that there should be a piles distortion. We're assuming that our electrons are really just, our atoms are pinned to their positions a distance a apart, and they can't make a piles distortion. So let's see what that looks like then. Let's sketch that. That our E of k is equal to alpha plus 2 beta cosine Ka. So if we sketch E of k as a function of k, then we have a curve that looks like this, running from minus k is equal to minus pi over a to k is equal to plus pi over a. And it's half filled, so our Fermi energy is here. Now let's think about what happens if we move the atoms further apart. So as we increase the spacing, the atoms are further apart, then their interaction strength between them goes down and the band narrows. So we still have the same cosine form of E of k as a function of k, running over the same minus pi over a to plus pi over a range. But this time, the band is narrower, and our Fermi energy now here, but it's still in the middle of the band, and it's still metallic. So we still have a half-filled band, which is metallic. Of course, you should remember that in this first case, where the atoms are close together, we have a strong curvature of the band. We have a small effective mass and a good conductivity, high conductivity, whereas when the bands are narrow, the curvature in the energy as a function of k is smaller, then the effective mass is large, and we have a poor conductivity, but we still have a conductivity. And we can keep doing this thought experiment. We can keep moving our atoms further and further apart, and we'll find that our band theory continues to predict metallic behavior even at very large interatomic spacing. And as we said at the beginning, this is unlikely. Eventually, the atoms are going to be so far apart that there's not going to be any conductivity between them. And in fact, what happens in reality is that at some critical spacing, the system will stop conducting and there'll be a transition to insulating behavior. And in fact, if we look at the resistivity as a function of the spacing, what we find is that this doesn't change gradually. It happens rather sharply, so that at small spacing, the system is a metal, but then at some critical spacing, it rather abruptly changes over to insulating behavior. And this, of course, is not what we see in our band theory. So this is a sharp transition. And it's often called a Mott transition after Sir Neville Mott. In the case where the origin of the transition is this electron-electron Coulomb interaction that we're going to be discussing next. Okay, so band theory is not giving us this behavior, which we know occurs experimentally in this scenario. And to describe this Mott transition, we have to go beyond band theory. And in particular, we need to go beyond one aspect of band theory, which is that it treats the electrons as being independent. So we need to go beyond this so-called independent electron approximation. And we need to explicitly include interactions between the electrons, and particularly the electron-electron Coulomb interaction. So of course, there are many levels of sophistication by which we could do this. We're going to do the easiest way. We're going to introduce the simplest possible picture of electron-electron Coulomb interactions. It's called the Hubbard model. And in the Hubbard model, all we include is the electron-electron Coulomb repulsion between electrons that are on the same atom. And those are the only Coulomb interactions that we include explicitly. It seems like this is a very crude approximation, but it's really sufficient to capture a lot of the physics. So before we start looking at band structures in the Hubbard model, I want to go back and start with the simplest possible scenario, which is the hydrogen atom. So let's start with the hydrogen atom and think about first the band theory picture and then the Hubbard model picture. So we know from when we solved the Schrödinger equation just for a single hydrogen atom, a nucleus, a positively charged nucleus with a single electron, we know that we get an energy for the lowest energy level, the 1s state, which is minus 13.6 electron volts. So if we want to draw an energy level diagram, for a hydrogen atom, it looks like this. Here's the energy. There's no K, there's no bands, there's just energy levels. Let's make the zero of energy up here. And at minus 13.6 electron volts, we have an energy level, which is the energy of the 1s orbital. And our single electron sits in that energy level. We can turn this around and say the ionization energy, the energy it takes to pull an electron out of a hydrogen atom, which we usually call I, then is plus 13.6 electron volts. We have to put 13.6 electron volts of energy in in order to remove the electron from the hydrogen atom. So in this simple picture, our kind of band theory picture, let's think about what electronic energy this picture predicts for a negatively charged hydrogen ion. Well, in our simple band picture, where we don't consider any electron-electron interaction, if we make an H- ion, the second electron is going to go also into the 1s energy level. And also have an energy of minus 13.6 electron volts. And so the predicted energy will just be 2 times minus 13.6 electron volts, which is minus 27.2 electron volts. And clearly this ignores the fact that the electrons have an electron-electron interaction. So in fact, the electrons repel each other. And the energy of the electron repulsion, which is often called U, in this case, we can measure to be plus 12.8 electron volts. So in fact, the energy for an H- ion is minus 27.2, the energy of the two electrons, plus 12.8 electron volts, which is much smaller, or much smaller in magnitude. It's only minus 14.4 electron volts. So this means that the electron affinity for a hydrogen atom to become an H- ion, the energy gained when a hydrogen atom becomes negatively charged is only 0.8 electron volts. It's the minus 13.6 plus 0.8 gives us 14.4, rather than minus 13.6 electron volts, which is the number that we would have for the electron affinity if there were no electron-electron repulsion. So the simple picture that we have had all through our kind of chemistry training, that we solve the Schrödinger equation for a hydrogen atom and we get a series of energy levels, and each of these energy levels can take 2 electrons, which sit in this orbital, is very naive in the sense that it doesn't incorporate this electron-electron repulsion between the electrons. So now we're going to look at another kind of band structure. Instead of the normal, another kind of band diagram, and we're going to at first stick with just the hydrogen atom again, that directly captures the electron-electron repulsion. So this electron-electron repulsion is incorporated in what's called the Mott-Hubbard band structure. And again, we'll start with just the atomic limit and sketch the Mott-Hubbard energy level diagram for the hydrogen atom. So we have an energy scale again. And we'll set the vacuum energy level at 0. And we know that the ionization energy is at 13.6 electron volts. So for the case where we have a single electron, then the energy level is at minus 13.6 electron volts. It's at minus the ionization energy. But in our Mott-Hubbard band diagram, instead of saying, okay, we put our second electron also in this energy level, then we have to remember that it has an electron-electron repulsion to the first, we directly incorporate that electron-electron repulsion in the energy level diagram. So relative to the vacuum energy, the energy level for the second electron, so the case where we have a nucleus with 2 electrons, we know is at minus the electron affinity, which is at minus 0.8 electron volts. So the second electron will occupy this in this band diagram, goes into the second energy level, the one that's at minus A electron volts of energy. And the energy difference between these two is the Coulomb repulsion, this 12.8 electron volts, which is the electron-electron Coulomb repulsion. So this is a very different kind of band structure. It's a band structure that directly incorporates the electron-electron interaction in its energy levels. So you don't have to incorporate that as a second effect later. It's a little bit unusual. It's not the kind of band structure that we're used to looking at. And then the lower energy level which is at energy minus I, is the energy of a singly occupied orbital. And the upper energy level this one here, that's at minus A, is the energy of an extra electron added to give a doubly occupied orbital. When we go on to discuss the band picture corresponding to this simple atomic limit, we will be calling these the upper and lower subbands, or the upper and lower Hubbard bands. And in this case, our gap, our band gap, is this U value, which is the energy required, or the energy of the electron-electron Coulomb repulsion. And it's not the same as in a simple band theory. I want to look at one more example of this correspondence between a simple energy level diagram that doesn't include electron-electron interaction and kind of Mott-Hubbard energy level diagram that does include electron-electron interaction, before we go on to talk about the band theory picture of both cases next time. So let's just take one more simple example and then we'll stop for today. So one more example. And I want to look at the particle in a box picture, the simplest problems that we solve in quantum mechanics. Again, looking in this correspondence between these two pictures. So first, let's look at the normal picture where we neglect electron-electron interaction. And we have our box. Of size L. And we solve the Schrödinger equation. And we have our first energy level, E1, with energy h squared over 8ml squared. And our second energy level, E2, with energy n squared, which is 4 times h squared over 8ml squared, or h squared over 2ml squared. And if we have 2 electrons, then both of these will occupy energy level E1, at least in the ground state. So both our electrons will go in the lowest energy level. And so the energy of the ground state of our 2 electron system will be twice h squared over 8ml squared in the simple band picture. And then if we want to incorporate the electron-electron Coulomb interaction, we'll have to remember to add U to that after the fact, after we've worked out the energy with our usual energy level diagram. So it's going to be h squared over 4ml squared plus U. The same problem in the Mott-Hubbard picture again will incorporate the energy of the electron-electron interaction directly. So the energy level for the first electron, E1, is the same as it was previously, h squared over 8ml squared. The energy of the second, E2 in this picture, is h squared over 8ml squared plus U. And our 2 electrons now, each energy level now can take just 1 electron. The first one goes into the first energy level. The second one has an energy which is U higher. It's the electron-electron repulsion higher in energy than that for the first electron. So in this case, we get the same answer. The energy for the ground state is twice h squared over 8ml squared, which is h squared over 4ml squared plus U. And in the Mott-Hubbard picture, we get this energy directly. We don't have to post facto add a value of U because it's incorporated into the energy level diagram. Okay, so let's stop there for today. And next time, we will extend this picture to solids.